for attending the last research session of ICFP. I'm thrilled to see that there's still so many people in the audience. For the final session, we will start with Jennifer Hackett, who will tell us about the most vexing problem, which is that when you want to reason about lazy evaluation semantics, everything is pure, but there's a lot of state under the hood, which really complicates the way that you want to think about your lazy programs, and in particular their cost analysis. So they're introducing a new way to reason about those semantics using Clairvoyant call by value.
Thanks. So yeah, I'm going to talk about how call by need is actually, well, can be thought of as a kind of call by value where you have clairvoyance. You can look into the future. So I've decided to illustrate that with a particular tarot card. This is the Nine of Pentacles, which represents having power, but also the wisdom of when to apply it. So yeah, what am I actually going to talk about? Well, I'm going to talk about, well, three things. Firstly, I want to talk about cost semantics, the mathematical models that we can use to talk about what programs actually cost. I'm also going to talk about evaluation strategies and how we might characterize call by need evaluation with the evaluation strategies by Haskell. And I also want to talk about what is we'd like purity, right? I want to talk about what purity actually means, because people talk about like purity means this, purity means that. You know, some people say you can't have non-termination. Maybe some people say you can. So let's think about that a little. And the angle I'm coming at all this is a thing called improvement theory, which is basically, it's an algebraic way to talk about relative efficiency. So by relative, I mean we're comparing programs. We're saying this one is better than this one. And by algebraic, what I mean is we're going to be studying the sort of nice algebraic properties of a particular relation, the improvement relation. And what that relation says is that if I'm given any context, then if I stick E in that, that'll cost maybe K. Then sticking E prime, I don't want it to cost more than K. I want it to cost at most K. In which case, then, and if that's, we quantify overall context, so I can say, well, in that case, I can always replace that E with an E prime. That's quite important if we want to talk about program transformations used by an optimizer. You know, you don't want the program transformations to make things worse. So if this property holds, then you can always apply that transformation. And in that case, we say that E is improved by E prime. Now, before I talk about call by need, I'm going to talk a bit about call by value and call by name. And these are they kind of differ in the way that we talk about the way we handle function application. So in call by value, if we want to apply f to x, first what we have to do is we need to turn x into some kind of value, a normal form. We need to reduce it until it's, you know, as simple as it can be, and then give it to f. And that's, you know, that's kind of easy to understand. Probably how you intuitively do maths on the page, maybe. And the nice thing about it is that the costs are compositional. So what that means is that if I want to know how much f of x costs to evaluate, I just need to find out how much it costs to evaluate x, and then how much it costs to apply f to the result of evaluating x. So just, you know, one number plus another. But it does have the drawback that it has a strict semantics. So divergence propagates. What I mean by that is that if x doesn't actually evaluate, if there's some error or if it loops, then we can't apply f of x to that. We need to be able to turn it into a result before we can actually apply a function to it. This kind of the opposite approach is what we call by name. And what we do is when we want to evaluate f of x, instead of evaluating x, we just give x to f as is, and then it will just substitute it in textually. You know, wherever there's an x, you replace it with the argument. And we don't care if it's in a normal form. Now, if x diverges, that still might converge. So that means we can work with things that diverge just like they're any other kind of value. But it does mean that we may end up repeating work between different if we duplicate that thing, we might end up having to do the same work twice. We don't like that. The solution, of course, is, well, a compromise, call by need, which sort of combines the non-strict semantics of call by name with this nice evaluate once property of call by value on the operational side. And we achieve that by sharing results. We just stick those results in a heap. And if we don't care about efficiency, that's the same as call by name. But there's a slight problem here, right? If we want to talk about the cost of something, we need to actually think about what's going on in this heap, about updates to this heap. And that's probably not something that you're quite particularly comfortable with if you're a pure functional programmer. So let's get a bit more specific. So this is sort of standard semantics for call by need is by John Launchbury, and it's based on 4 rules. The first rule says that if we have a heap, gamma, and a term that's a lambda abstraction, we say that's done. So we just evaluate that, and if we just immediately return the same heap and the same term. If we have an application, then and note that I'll get back to why that's applied to a variable rather than a general term, but if we have an application, we reduce the function to a lambda abstraction, and then we just sub in the thing. Like I say, I'll get back to the fact that it's a variable. The way we actually share work is with this let thing. And what we do is we just move that. If we have a let binding, we just move the thing we're binding into that heap. And now if you want to be able to apply a function to a general term, you can just let bind it and then give it the variable you found. And finally, if we have a variable, we can look that up in the heap, evaluate it, store the result of the evaluation in the heap, and then we return a alpha renamed version of it. You can sort of ignore that bit though. Like I say, this is the issue, right? We've got some heap updates. There's an effect happening. There's something impure in our pure language. But before I get into how to fix it, I'll just show you. If we want to talk about costs, we can just count the number of steps, or you can think of it as the size of the tree, not counting the leaf nodes. Now the question is, because this is, like I said, this is kind of impure, these updates are kind of important to what's actually going on. But maybe they're not that important because the actual results are kind of abstracting away from that impurity. So maybe we can be a bit sneaky. Maybe we can construct something that's equivalent but feels purer in some sort of hand-wavy sense that I'm trying to imply with those quotation marks. And you might ask, well, does it matter? Well, I think it does. And here's a good example. If you think about common subexpression elimination, you've probably seen it before. You've got an n in some complex thing that appears maybe multiple times, and you just want to play it out into a letter binding. You'd think that's fine. That should never make things worse. But it's actually kind of hard to prove. And there is a paper that goes into this, but they go into quite detail. And frankly, I'm not clever enough to follow that paper. So I want a simpler way to think about it. The other issue is that if we want to think denotationally, like so far I talked about operational semantics, but maybe we prefer denotational semantics. And if we want to think about that, then we basically have to work in a Kleisby category. We have to thread state through absolutely everything we do. And that just, everything gets very hairy at this point. So what do we do when things are murky and unclear? Well, we look into the future. And what I mean, if we somehow had some way of working out which subterms of our program actually needed to be evaluated, then we could just do those and we'd get rid of the rest of them. That's the dream, right? Like that's when if you're taught lazy evaluation, you think that's how it works. In your head, that's how it works. It's not how it actually works, but in your head, it's doing magic. But how do we do magic? How do we make magic real? Well, we can borrow a trick from automata theory. So a non-deterministic automata, you might recall, can be thought of as a normal kind of automata, but it has like a magic. You can ask magic 8-ball, which way should I go? It can just guess the right path to take, and if there is a path that works, it'll take it. And by analogy, maybe we can work with a non-deterministic semantics to achieve this. So let's see what happens. This is what we had before. So firstly, we're working in call by value, which means we need to change the let rule. Let at the moment just pushes things into the heap without evaluating them, which of course, that doesn't work. We have to evaluate them. But now, of course, you see the variable rule was evaluating something, but of course now we know that everything in the heap is going to be a value. We can simplify that. And of course, this is just normal call by value. If we want the clairvoyance, we have to add the option that we skip things. And of course, this is ambiguous. If you have a let binding, then you don't know which route to take, but you can look into the future and work out which one's better. But of course, and the nice thing is there are no more updates. So we've kind of replaced. You can think of it as we've replaced one effect, that of state, which is kind of awkward and difficult to think about, with another effect, non-determinism, which is maybe slightly nicer to think about. And we can actually prove that this is equivalent to call by need. I mean, that's what we wanted, right? We wanted a better way to think about call by need. So here's the theorem that proves, well, here's the statement of the theorem. You'll have to look in the paper for the proof. That if I have a term E and a heap gamma that consists only of values, and it needs to consist only of values because otherwise it doesn't make sense in the clairvoyant call by value world. But if that heap and term take k steps to reach a value in call by need, then there is some evaluation in the clairvoyant call by value world which will take those k steps. And on the other hand, if you can evaluate it in k steps in the clairvoyant call by value world, then there must be some way to do it in the call by need world, but you might be able to do it, you can do it at least as well. And what this actually means together is that the call by need cost is the minimal clairvoyant call by value cost, which is kind of what we wanted. We wanted, if you magically picked the best route, you would get the right answer. And of course, as a corollary, we know that this improvement relation that I showed you before is it's going to be the same relation regardless of which semantics we're actually in. Now, let's try applying this to some of the problems we had before. Common subexpression elimination is actually a lot easier to justify. Just think about it. You just sort of think about what could happen. Well, if the whole in that context doesn't get evaluated, then we can just skip, and that's fine. Otherwise, that let is definitely going to let us share some work that we did that we would have not maybe repeated before. So that will not degrade performance either. And it gets better because we can use this to give a sort of denotational semantics that avoids heap nastiness. And the trick is basically we work in a domain that lets you join things like a lattice, and you can just interpret let binding as the join. It's taking the best of both worlds out of discarding and evaluating Ely. And then if you have that, then your semantics is going to be sound for that improvement relation, meaning that if the interpretation of two terms can be compared in the order of the lattice, then you'll have that contextual improvement. You'll know that it's safe to replace one with the other. It doesn't necessarily go the other way around, because that's full abstraction, that's a hard problem. And it's probably not true in this case. But, it does give us some, it does mean that we can prove some things starting in this denotational world and then transferring the results into the operational one. So, let's conclude. You think you need updates to reason about sharing? Well, you actually don't, it turns out. We can construct an operation semantics that doesn't use updates, and it gets cleaner, and it's still faithful to these efficiency concerns that I actually care about. I want my programs to run in some kind of predictable way. And that also gets us this nicer denotational semantics. Any questions?
All right. Before we move into the questions, I see that some people are standing in the back, so if you're on the edge of your row, if you could please move in towards the center to leave some space for the newcomers. All right, we'll start with a question from Slido. Someone asks, if call by need is clairvoyant called by value, what is clairvoyant called by name?
That is a good question. I suspect clairvoyant call by name is just call by name, because it's just like in call by name the question is, where are you going to make those decisions? So if you take those rules of call by name, you've got to add in some. It's just going to be, I think it's just going to be call by name, but it might fail occasionally, but then if you do the whole taking the best case scenario thing, it just becomes call by name again. So probably doesn't do anything interesting, but it might do. Who knows?
All right. Any questions from the audience? Yes, over there.
So you described very nicely why this might be appealing by getting rid of the updates and the operational semantics. But of course, the proof of the pudding is in the eating. Your goal is to make programs easier to reason about. So there's quite a bit of work, isn't there? Like in David Sands ages ago did all this improvement theory stuff that you're basing off. Have you been able to take any proofs that he or other people have done about that this program does improve that, and show that that same proof comes out much more easily or conveniently in your framework?
So yes, so in the work of Dave Sands and Andy Moran, there's a bunch of rules basically given for improvements between call by need programs, and we've not done all of them because there's quite a few, but we've shown how to do a few of them in this new sort of setting, and they seem largely to be simpler. And that's in the paper if you want to look at that.
Okay, cool, thanks.
We have another question from the audience here.
In general, I tend to consider that the heap-based semantics of call by need is kind of old school, and that what we should use instead is the local heap presentation that has been given quite famously by two groups of authors at the same time, Phil being one of them. Have you tried to look at what your clairvoyant presentation becomes in this time?
So I haven't. I don't know if it does anything. I don't know if I suspect it's going to be largely the same, but I guess you've got more scope stuff going on. It's an interesting question, and I'll have to think about it.
Okay. We have a question from Slido. Is call by need semantically equivalent to memoized lazy evaluation? Would that imply that this is arbitrary to add to any lazy functional language?
So I wouldn't say call by need was equivalent to memoized lazy evaluation. They are two different names for the same thing in my book. So yes.
That was a very efficient answer to the question. Thank you. Do we have any other questions from the audience? All right, well, let's thank the speaker again.